Hello, gentle readers. September 24, 2025. Here from a study with Ross Finlayson is Logos 2000, 21st Century Foundations. Today, I will just be kind of going through the box of these books that I've collected and getting an idea kind of from their content and their subject matter, what is kind of the consideration. And I haven't fully read all of these books, but I kind of read very readily. And so when I collected these, it was with a goal and an idea that as I surveyed them or scanned them, leafing through the pages, what I arrived at was that they have a very much amount of perceived value and relevance and a lasting and a standing relevance to the fields of the science, for physics, the natural science, and all the things that come from that, chemistry, biology, all the hard sciences. Then that as later it would be incorporated their considerations, the idea is to help relate what are their considerations to, in this fuller, wider dialectic, others, and to look for commonalities, and then also to look for where in the decisions of the theory and the developments of the theory that there are common points of revisitation, that being the usual idea that some decisions left other alternatives considered behind, and they find themselves again when later the entire theory is being reconsidered, to revisit as is reconsidered, is reconsideration, revisitation, that otherwise would lose the context overall and end up to old wrapped as new and circular arguments and these kinds of things. So not much to it, very much, but just an idea to kind of look through these things and get an idea from their subject matter and content, how they would relate to other aspects of this pretty wide field of foundation, so like the theory of everything, and then the premier theories, and then their datedness or what still stands as their contribution, and these kinds of things. So I'll just grab randomly from the box of books. Proximity and preference, problems in the multidimensional analysis of large data sets. College and Rayner, editors, Minnesota Press. Or Golledge, excuse me, Golledge, and Rayner, Rayner. So this book appears to be from 1993 or so. Golledge is from UCSB and Rayner's from OSU. It's from the Minnesota Press. This is from 1982. Substantive and methodological aspects of the interface between geography and psychology. So one might associate that with is substantive and methodological aspects of the interface between geography and psychology. There's geography as of the communitarian, and I don't like the word community because it reminds me of communists, and I'm not too much into fascists. It reminds me of fascists, and I'm kind of a capitalist, but that's just because it's considered the most egalitarian, the entire free market enterprise thing. Well, there are yet controls, and there are safeguards, protections of the peoples, protections of their rights, their individual and collective rights, and these kinds of things. That's courtesy to geography, not because, for example, I grew up in a mountainous and desert region, yet with natural resources and water, but that I grew up in the United States of America, and so that geography is also associated with a nationality, say. And I don't like it when it's usurped words that have considered good values, like conservative and liberal, both those kind of being considered good ideas, both being Americans, say, vis-a-vis people saying that they're like progressives this or progressives that, when it's like that's just radical, and it's not bicameral so much as bipolar disorder, and these kinds of things. So that's some of my psychology say. So as with regards to the substantive and methodological aspects of geography and psychology, it would be both with regards to the demographics and then also with regards to simply and plainly the geography. They find that people who inhabit an area that's way, way above sea level have a different sort of mindset than people who live very close to the beach. And these are the kinds of ideas and things that could be part of this introduction to this series. And so then looking at this, it's about the multidimensional. And so in terms of studies, and then this gets into what you can consider the soft sciences, but it's still addressed with statistics as the only sort of fair rule to arrive at this statistical methodology being, according to our philosophy of science and statistics, invalidating the null hypothesis, say, or falsifying the theory, and not so much confirming it or confirming it, or that something was predicted so much as it's not unexpected. That when I see loose language about statistics and physics, it kind of reminds me that the entire empirical mindset is very well ingrained in people and very inductive, and it's the easiest sort of argument to make, that it's the easiest sort of argument to break, yet that it's unfortunate and sad that the invincibly ignorant, according to their inductive empiricism, can't be convinced any other way. These things. Experimental design and measurement problems. So measurement problems involve both the gathering of the data and that eventually gathering data interferes with the thing. Like if you want to investigate an anthill, so you dig it up, and it's like, well, now there's a hole in the ground, but to the ants, it's entirely destroyed their colony. And so then trying to figure out, well, it's like, is that a fair representation of a way? It was said that was, counting how many ants or seeing how they react from having a pile of sugar nearby. It's like, well, no. And so this gets into the ideas about the design experiment and controls, and the idea of that all these different factors include all these other different factors. And so it's like when you take a survey or someone gives you a survey, all I know is whenever anybody gives me a survey, I politely decline to answer the survey. So then what ends up happening is the surveys are full of survey takers. And it's not so that everybody's a survey taker, yet it's so that they have their own opinions, but it's just not necessarily the overall so that they care to take surveys. So in these sort of statistics and scientific experiments, but overall interactions, because the subjects and the experimenters are both people. So they're essentially all in one big experiment together. And then it becomes, matters of motivations and all these kinds of things, but more so concretely, the actions that it's going to vary a little bit in terms of being able to look at any kind of experiment, and also that the entire lab is part of the experiment. And so then when looking at how these things happen and what were the motivations behind it, and conformity of consent and these kinds of things, and informed consent is what I meant to say. That these are the kinds of things with regards to, it's like, well, can we really inform them if they would have to study for these years to understand what's actually being done, or can we really inform them without subjecting ourselves to legal liability? And I'm just kind of framing this in terms of things that I might think about if I were to take part in the design and implementation of experiments on people, which I don't. I just think it's easiest and fairest and the least amount of emotional and mental baggage for me to just say, hey, people are people, and then that we can't all get along too, and these kinds of things. So anyways, surveying multidimensional measurement, interactively ordering the similarities among a large set of stimuli. So this is about ranked statistics and ordering statistics, say. Department of Psychology, Chapel Hill. Incomplete experimental designs for multidimensional scaling. So this helps incorporate the fact that these are just statistics, and so they can't really be said all the different things about it that would be so as like the voluntary application or people building something together, in a sense. Sampling designs and recovering cognitive representations of an urban area by Spector and Revisitation. out of Alabama and Queen's University. Considerations in the selection of stimulus pairs for data collection and multidimensional scaling. So these stimulus pairs and the data collection and multidimensional scaling by Isaac out of OSU and Young, Null, Sarl, and Hoffman out of Chapel Hill have that. I imagine I'll look at this paper from Isaac out of Chapel Hill or Ohio State. The interface between the types of regression and methods of collecting proximity data. Data theory and problems of analysis. Recovering the parameters of a decision model from simulated spatial choice data. A revealed preference analysis of intra-urban migration choices. Data problems in the application of conjoint measurement to recurrent urban travel. Applications of functional measurement of problems in spatial decision making. Some remarks on multidimensional scaling and geography. Comparing objective and cognitive representations of environmental cues. Recovering the dimensions through multidimensional scaling. Remarks on two problems. Issues in data collection and reliability and marketing multidimensional scaling studies. Implications for large stimulus sets. Suggestions for identifying sources of unreliability in multidimensional scaling analyses. So on page 80 or so, right before the paper of Araby and Soil, or Arabi, and here's Isaac, and he's talking about considerations in the selection of stimulus pairs for data collection, multidimensional scaling. Says the problem for multidimensional scaling is the rapid increase in the number of distances, and choose 2 as the number of stimuli n is increased. So this gets into clustering and means and principal component analysis, gradient descent, and then also the generalized linear model. The gradient descent is a great thing to try and look for which way things are going. The generalized linear model and the principal component analysis are two fantastic methods available to analysis given data to find patterns in the data. And really the principal component analysis then first helps find different clusters of data to help find different subgroups of populations where distributions according to the multidimensional scaling would more likely be accurate. But there's any number of ways to look at that as with regards to individuals that is kind of like as after Nelson Goodman's the calculus of the individuals and these kinds of things that statistics has a lot going on that it's at a loss to discover these relations except as from treating everybody individual and the same. And then with regards to inventing the experiment that could actually sort of make that so is sort of as a voluntary and participatory and honest effort, and it's hard to figure and sort that out, and any sort of means to try to extract that kind of information would itself be subject to its own interference with itself in the experiment of the data. So and so far as that goes, then it just goes back to the usual idea that you take somebody on their word. And so you have certain expectations of mores and norms, and so with that you can accept or believe that someone's like they're not a criminal, they're not an axe murderer, they're not out to get me, and insofar as their word is good. And then if they arrive at they say, you know, I was like I like apples on Saturdays but peaches on Sundays, you know, whether to figure out what that would entail for preference in these kinds of things is largely for a matter of what people would vociferously make for themselves, and that otherwise it's kind of surreptitious, and sometimes that's the only way things can be done. There's a whole black box aspect, but then trying to figure out when there are many of these kinds of knobs to dial, and then dialing too many knobs at once, it can only give kind of a gross estimate, and will also often increase the noise on all the other relations that hold people together or that relate among them. So it helps to define that, yeah, this is the problem, because we are not just lab rats, and essentially the controls cannot be established. And so then that basically is to describe that there's an entire introduction for something like the central limit theorem, that besides one standard deviation being like, okay, 85% is going to be in this confidence, it's more like 65%. So there's, for large populations and uncontrolled populations, it basically changes the usual model of the central limit theorem for statistics. That's the thing. For designs involving direct judgment of similarity, the solution seems to be to reduce the number of pairs actually judged. And so then as that's a smaller proportion of the actual population, then it's just identifying this cohort or subpopulation, and then it's kind of reduced. And so then that aligns with geography and aligns with time series data, meaning, well, you can reduce all three problems at once, but at the same time, then it's windowed and boxed that in there. And while that may refine the analysis in that region, it doesn't necessarily leave it in a good place or coherent in the wider setting. Two approaches previously taken have been the use of interactive scaling, which involves online participation of a subject with rational selection of pairs based on previous responses, and the use of cyclic designs to delete pairs a priori. None of these approaches is altogether satisfactory. Interactive scaling because of the online requirement, and cyclic designs for reasons discussed below. So I'm not too sure exactly what is the vocabulary here with regards to the presence. Online usually just kind of meaning the presence. And then this cyclic designs as relating to the empirical, and whether it's not meant to be a surprise, or it's not a tabula rasa, the blank slates off which probability is with independent and identically distributed random variables has, as with regards to the independent and the identically distributed and the random of the variables. So it helps to reflect there's a difference between statistics and the study of cohorts and populations. So anyways, as you might imagine, then this book is full of case studies and some of the mathematics and a very descriptive account. Then with regards to usual sorts of statistics and some functions, the preference function, to the MDS routine TOR-SCA. So with regards to SAS and SPSS, statistical analysis software, and SPSS, the two usual major statistical analysis environments in the computational that would have been as of this time, but also these kinds of things. The references then are, as according to each of these papers, have their own references. And with regards to some statistical considerations in multidimensional scaling by J.O. Ramsey in 1969. And Spence and Damoni, single subject incomplete designs for non-metric multidimensional scaling. So this is an example of one of these books around here, and then trying to figure out what it has to do with psychology and with all these kinds of things it is what it is. Notice the nice sunburst behind here. There's discussions here of the behavior of light and all these kinds of things. Medical Embryology by Jan Longman. And so embryology is the study of the embryo. And so in zygotes, like mammals, the zygote is the fertilized zygote, as in the course of human or other mammalians, sexual reproduction. And then the embryology is the study as the development of the zygote as with regards to the blastocytes, the pluripotent, multipotent, and totipotent stem cells, kind of in that reverse order, the totipotent and the pluripotent, and then multipotent. It kind of varies between after totipotent, which is like it's undifferentiated. It differentiates anything according to environmental factors, and then the pluripotent and pluripotent and multipotent stem cells, which resolve to they become this kind of cell or that kind of cell according to the environmental factors, usually of the amniotic sac and the north and south, essentially at some point reflecting after the clumping and the development and the cellular division and all these kinds of things, the head and the tail and these kinds of things. So this book once belonged to a guy named Charles Hammond, H-A-M-O-N. Medical Embryology, Baltimore, the Williams and Wilkins Company, 1963. The cover illustration is La Main de Dieu, The Hand of God, by Auguste Rodin, 1897. The hand is shaping a massive formless matter from which, as from a womb, emerge the bodies of man and woman. Reproduced with the permission of the Philadelphia Museum of Art from a charcoal sketch of the bronze in its Rodin Museum. Rodin, of course, is most familiar for The Thinker. And the way we were exposed to Rodin, the Thinker, is when we were children, is there was a cartoon where these animals were fierce rivals and enemies. And so the one would chase the other. The cat would chase the mouse, and it usually ended up badly for the cat because the mouse in its evasion of the cat would run it through a construction yard or something like that. And so it ended up that or the dog would chase the cat. Either way, you know, the big fish eats the little fish, but in these ones, it was always kind of a moral example that doing so led to bad outcomes for these bullies of a sort. So, anyways, the thinker was just the shape of the man in repose with his chin on his hand, and then he's thinking, you know, and he's kind of navel gazing, as it were, by Auguste Rodin, a very well renowned sculptor, and it's then this is also like so. So then he says the study is recent advances in embryology, radioautography, and electron microscopy have been so overwhelming that the medical student often has difficulty in grasping the basic facts of development from the highly complicated picture presented to him. So the study of this belongs to, just go to the university library and find the A section, and that's biology, and there'll be 100 books in a row, and they will describe the entire course of development of the zygote to birth, and it's very well explored and documented. At least one good example of that. As with regards to, say, vaginal birth and the cesarean section, and the fact that the cesarean section has become so widespread, as with regards to, you know, the development of what becomes an individual, and the dreams, it enters in this brain a dream state after about halfway. That it's these are the kinds of things that are very well understood, but everybody's different, so it could be many things, many ways. But largely, the humans are very much alike. You know, 5 fingers and toes and all that kind of things. Not always, compared to like 2 heads or all these kinds of variations of things with regards to the species. That's not so relevant here, but just give you an idea. This is a medical book, and then it's described similarly to the Gray's Anatomy or something, like all these different kinds of the systems and their developments. General embryology. Geophysical data analysis, discrete inverse theory. So this, I probably, when I got this, I saw discrete inverse theory. I thought that would be a great idea because it's based upon a macroscopic type of thing. And this is one of Deo's books. He's a Boeing engineer at some point in time. And what it has is this, in this discrete inverse theory from Academic Press in 1984, it gets into formulating inverse problems. So here, if you follow these talks, you know that the principle of inverse is a big deal, and so that this is a way to set stuff up with, which is otherwise just not just intractable, but hits a wall and would just go either way entirely wrong, the one or the other ways. So setting up the inverse problems is a key kind of thing. So describing inverse problems, some comments on probability theory, solution of the linear Gaussian inverse problem, and solution of the linear Gaussian inverse problem, generalized inverses, ... maximum likelihood methods, non-uniqueness and localized averages, application of vector spaces, linear inverse problems and non-Gaussian distributions, nonlinear inverse problems, factor analysis, sample inverse problems, numerical algorithms, and some appendices. So this is a pretty thorough book, and it gets into a lot of different methods, and these aren't generally what are given as the things, but it does mention some things. I was looking at antenna theory, and so what it talks about here is side lobes in the Backus-Gilbert spread function. So the Gilbert circuit is related to, what was that field? Baca, that guy Baca or something like that. He invented some circuits that were kind of like Fourier analysis, and was with regards to the antenna. So the Gilbert cells is that one. And so, but then when it mentions side lobes, has this whole thing to do with the sideband. So in one of the last episodes, the discussion was like, well, for the entire electrical theory, there's Maxwell and E cross B or D cross H, depending on when you ask Maxwell. And Maxwell had a couple different ideas, which really should come first to those, and the other be derived. Then there's a whole spiral wave theory. It's like, well, those are just, you know, lines of force that are kind of concentric or as of lobes about these poles. But then there's another way to look at it that's always only ever moving, and so there's a spiral that grows out of it, and then only when it comes to rest does that kind of come to rest also as well, and whether there's anything that's ever really at rest. So The side lobes, with regards to the radio frequency radiation, with regards to that having kind of this high and low component then, I mean, when we're talking about electromagnetic radiation and optical light being special, then the usual idea, well, it's like up here it's high band and back down here it's low band. And that's heat, and above there it's electricity and radio. And also up there, way up there is could be X-rays or Roentgen rays. They're different, but we just say whatever the energy comes in, that's their wavelength, and that's their frequency, and then that's their energy, and then light's in the middle, and though it's massless and chargeless, we're just going to call it that anyways. Though there's no way to say that it doesn't disturb the field if it doesn't disturb the field, or that it does. These kinds of things that this would be something to look at and explaining why this fellow has for the solution of the linear Gaussian inverse problem, generalized inverses. The generalized inverse is a great sort of thing because it's kind of like, well, the inner product is like a scalar product. Well, what's its inverse? Well, its inverse is the outer product. And it's like, well, what does that say? It's like, well, it's kind of outside this box we drew, so we don't like to talk about that because that's where the sidewalk has ended, and there's dragons on the map, and we're not sure exactly what to say about that. So these are kind of things getting into why the inverse in like the space inversion bit is such a powerful technique, because it's always present in these kinds of things. Every researcher and the applied scientist who has analyzed data has practiced inverse theory. Inverse theory is simply the set of methods used to extract useful inferences about the world from physical measurements. Fitting of a straight line of data involves a simple application of inverse theory. Tomography, popularized by the physicians CAT scanner, uses it on a more sophisticated level. Now, this is Menke here, M-E-N-K-E, William Menke, if I'm pronouncing that correctly, and I hope I will. The study of inverse theory, however, is more than cataloging of methods. So let's see if we can define what inverse theory is. Being introductory in nature, the book deals only with discrete inverse theory, that is, the part of the theory concerned with parameters that either are truly discrete or can be adequately approximated as discrete. By adhering to these limitations, inverse theory can be presented on a level that is accessible to most first-year graduate students and many college seniors in the applied sciences. Treatment of inverse theory, let's see if it defines it. Inverse theory is an organized set of mathematical techniques for reducing data to obtain useful information about the physical world on the basis of inferences drawn from observation. So this is like our severe abstraction and our mechanical reduction and all this kind of stuff. So that's kind of covered a lot with regards to the continuous and the discrete. And then with regards to getting back from the continuous and discrete is like continuous inverse theory here has that gets involved the non-standard besides just the nonlinear. Here the super standard and the extraordinary. So that would be a thing, and if we ever got around to kind of defining what that is, it's kind of living in this world. The term inverse theory is used in contrast to forward theory, which is defined as the process of predicting the results of measurements, predicting data on the basis of some general principle or model and a set of specific conditions relevant to the problem at hand. So, crunching. Inverse theory, roughly speaking, addresses the reverse problem. Starting with data and a general principle or model, it determines estimates of the model parameters. So, science. So, this is saying that given the formula and crunching the numbers it's what's called forward, like forward inductive inference, and then this inversion theory or inverse theory, as the author puts it here. And I'll have been influenced by this. I mean, I've had this book for a long time, although the first time I came up with the idea that the first axiom, if there was any at all, was inverse, was at least 30 years ago, and I don't remember anyone particularly telling me that. But it's probably after studying things like, well, the East and West are inverses in their philosophies, and then like the one has a beginning and no end yet, and the other one's like it's always formless or void or the null and universal, and these opposites and universals, it's like, well, it's got to be both somehow. The inverse is then relating that also to consciousness, is just turning over the inverses. So anyways, this is geophysical data analysis, discrete inverse theory from the early 80s. So here's some books from a common press here. This is John Wiley and Sons from New York. Methuen's Monographs on Physical Subjects, Magnetism, by E.C. Stoner. So this is Stoner's Magnetism. Methuen's Monographs on Physical Subjects, the meter-kilogram-second system of electrical units, by R.K. Sass and F.B. Pittock. John Wiley and Sons, New York. So these kind of go along with the university press mathematics work, so they fit in this same pocketbook size. General editor B.L. Warsnop, BSc, PhD. And so these monographs include the kinetic theory of gases, photochemistry, atmospheric electricity, molecular beams, cosmological theory, the conduction of electricity through gases, low temperature physics, high voltage physics, fine structure and line spectra, nuclear spin, infrared and Raman spectra, thermionic emission, mercury arcs, method of dimensions, applications of interferometry, the cyclotron, wireless receivers, special theory of relativity, the Earth's magnetism, alternating current measurements, dipole measurements, fluorescence and phosphorescence, X-ray crystallography, electromagnetic waves, physical constants, collision processes in gases, the commutator motor, the general principles of quantum theory, thermionic vacuum tubes, relativity physics, the physical principles of wireless, wave mechanics, thermodynamics, and introduction to vector analysis for physicists and engineers, Heaviside's electric circuit theory, electron diffraction, waveguides, wave filters, atomic spectra, magnetism, and X-rays. So this one is meter kilogram second, and so it's the new one, I guess. High frequency transmission lines. And this one is magnetism, so I expect to find in it kind of this same outlay as if it's not quite reached this point yet. Oh, no, well, this already included, that was the fifth, and this is, the sixth is already included. So this is the fourth edition by Edmund C. Stoner, SCD, FRS, Professor of Theoretical Physics at the University of Leeds, produced in London, fourth edition, 1948, first published 1930. In this book, I have aimed at describing briefly the present outlook on certain aspects of magnetism. The second edition, the book was completely revised. For this, the third edition, there are fewer changes. Rapid advances were being made in many directions. So, magnetic properties of atoms with regards to ionization and charge and polarity things, diamagnetism, paramagnetism, ferromagnetism, magnetic properties of elements. So this gets into like reactance and remnants, susceptibility, permeability, and otherwise these things are like, well, what are these numbers for? It's like, well, you know, the fluid model as if it were like so, that it was, electricity was like so, and then it crosses the magnetic lines, so moving one moves the other, and that's kind of like Faraday's law, or what it is. It's like, well, yeah, and then there's Ampere's law too, and that means current, it's about current and displacement current too. And it's like, well, so it's like a fluid, right? Yeah, it's kind of like a fluid in the middle if we ignore the edges. And then there's the skin effect and core effect with regards to current, electrical current, and then with regards to magnetic current, or the changes in the magnetic field strengths and these kinds of things, is that then these different materials, they do and don't kind of absorb water. It's kind of like, well, it's kind of like the fastest way for any liquid to go is through vacuum. It will naturally just be kind of impelled into a vacuum as via like a pump on the other side. And so the idea is to think like, well, it's like actually a conductor is like one big atom, and so for the electrons to jiggle their way across in their kind of zeros as they are of the charge moments, about the fact that the electric charge to mass ratio is kind of arbitrarily large, and that then the amount of charge or the movement of charge usually in current is like just the movement of the holes is in the model of the electron, and point charge and Leonard Weichart and all these things we learned in college, and everybody in engineering learned these things at one point. This gets into why these different kinds of magnetism have like, well, they're kind of like physical properties of liquids in the fluid model, and they're kind of opposite, and at some point in time it's like infinity opposite, so I guess that's inverse for sure. And then trying to figure it out. Then the spiral wave thing is a good way to kind of help model that, because otherwise waves would be a perfect model of change in an open system, and then in the spiral wave it helps to, it was like, well, there's got to be flux somehow getting back out. I mean, we've squeezed the balloon, and it's got the whole world to go to. So, and then if it can't be like any particular direction once, it's got to be spiraling its way out, kind of is the idea. So Descartes' vortices, Descartes' theories of motion, Kelvin and his vortices, the theories of the electricians, and they're having seen these like, oh, I made an electron beam, and now I know it's like with the Helmholtz coil, you can make the Helmholtz spiral and just make spirals like dance all over the walls and stuff like that. meaning it's well known that electricity naturally has these effects, but it's not in the formulas. See, so and it doesn't matter. It's like, well, it just stays on the wires, and then it goes out to the wires, and magnetic fields off that make for the radio waves when it's collapsing and stuff like that, and the resonance. These are the things, and these are the more of the things, kind of. Old and new quantum mechanics. In the earlier quantum theory of atomic structure, the extranuclear electrons of an atom, regarded as concentrated charges, moving in orbits about the nucleus as center of force. If this conception is to be retained, the stability of atoms indicates that electrons, though accelerated, cannot radiate energy continuously, as the classical theory would predict. They would fall in to the atom. Non-radiating stationary states must be possible, and Bohr extended the original quantum theory to fixation of these stationary states. So he inverted it. And anytime you see quantization now, or making something discrete out of that kind of, you can just kind of say it was, or picking a principal branch, as Gauss is so famous, is successful for. You can say it's like, well, that's an application of abstraction and inversion. And then from then on, you can give that to everybody. It's like, now just carry that forward. Because the idea is like, well, these are the kinds of things that you could carry backwards, that if you carry that forward, it's breakable. So you have to figure out this whole kind of account as to why those things are like so. Non-radiating stationary states must be possible, and Bohr extended the original quantum theory to the fixation of these stationary states. So saying must be possible is like, we don't know any other way to say they do. And then that it would be like this non-classical, superclassical again, somehow just extraordinary and very ordinary just by the means and the nature of these things, that is like, we have to take into account that it's like it's from all the way to the left, bounces off the middle and goes all the way back at every instant of time. It's an instantaneous infinitary kind of process to have any kind of this relation of two things in a space altogether at once at all. Otherwise, usually, besides the particle theory, the whole idea these days usually is like, well, what's physics? It's a field theory, meaning our field has fields of force and lines that are always constant, meaning up to date in time. They're always contemporaneous. They're always evaluated and current. The field lines of these forces a function of time then, as well as you can read from that statement. So then the idea is that what's a field theory? And then what happens is like, well, imagine something spinning around in a ball. All of a sudden it's lost all relation to anything in the world, which is now spinning around it as much as it's spinning around by itself. So it's a gauge theory, they say. Well, then they say, well, what's the real gauge? I mean, how do we measure this curvature of the universe? It's like, well, if you have a spiral space-filling curve, that is, its curvature is 1 over r. So that kind of is, under and over the inverse, the real curvature of the universe. So the spiral waves, again, are very physical. So it's not just like a good idea. It's like line drawing is like a spiral wave in 0 or 1 dimension. In 2 dimensions, it's the only way. All I have is a pencil. All I can do is scribble a dot without ever crossing the line, without ever going outside the line, filling it out until I made a disk. It's a spiral space-filling curve. So the spiral wave is mathematically about as primitive as you can get and make a continuum out of an origin. So it's central, it's primary, it's kind of elementary. And then we can get from it stuff like Euclid's geometry, and so then it also is saying a lot. And also, from the line rules, you can get the fundamental theorems of calculus, as if that weren't enough, just in case you needed kind of like the least amount of theory, because then you can call that an inversion or a severe abstraction, and just get that it just gives all the rest of what's usually called relevant in mathematics. So that's real. Yeah, okay. So, and then he's talking about for periodic systems, the fundamental postulate may be expressed by the equation, the integral of P dq equals nh, where the integral is taken over a complete period. P and Q are conjugated momentum and position coordinates. So the conjugated position momentum are like inverses of each other, see. N is an integer, and h is a Planck's constant. For an electron describing a circular orbit, this is equivalent to stating that the angular momentum must be an integral multiple of Planck over 2 pi. So that gets into Planck over 2 pi, Planck over 4 pi, and these kinds of things. with regards to these things. And the old mechanics, and then later the new mechanics, where it's like, well, how about it's just everywhere? There's no more electrons anymore, and so, but we're just going to say everything's momentum again, even though it's not a conserved quantity in the angular, and we're just going to say that all our point particles, which are not really points, but they have to be finite somehow. They can't have position and momentum because they can't really have position because there's no center of them. They can't really have momentum because it would all be angular. Well, but these are the numbers that are going to add up for us, according to electron physics, and exactly what we define as charge to mass ratio, in terms of a perfect idealized conductor and these kinds of things. The difference between, I guess, the ideal components in electricity and the electrical and real world components or practical components is quite large. And so this in the signal theory and all this kind of stuff is like, well, what's our ideal curve? It's like, it's a spike. And okay, what's the practical curve? It's like, it is noise, maybe a spike, you know. So trying to figure that out gets into these things like this, the Gilbert cell and this for tuning antennas. And then as something was mentioned here about the mercury vapor, is the idea that mercury makes a really good arc. And so for something like the thyrototron, which is the idea of, take a DC electrode and so you point it in the center of a ring magnet. So the edge of the electrode, with a high enough current arc, it will arc to this magnet somehow, or just according to being a magnetic field, it will arc in that direction. But because of the Lorentz force and the idea that will gain a handedness and a spin around, it will make a rotatory motion of this arc. And so the idea of the thyrototron is this kind of idea of an invention I have, is you make one of these and then you have to make it so that's kind of a sealed apparatus, and so it can't disintegrate like an arc welding apparatus would do, the thing. But you can just have it in a magnetic field like a ring magnet, which is cheap and you can get them in bulk, and an electrode, which is a piece of metal, and of course is by the pound, and electricity, which is any kind of DC at a sufficiently high voltage across the arc gap, which can be arbitrarily small. Then when trying to convert power from direct current to alternating current, or to invert the power inversion from DC to AC, you want to have it so that you get out what's called a smooth sine wave, and they call it pure sine wave, but this is usually just put back together from having blasted all these pieces with the silicon controlled rectifiers or MOSFETs or IGBTs, that insulated bipolar gate arrays or whatever they are, switches in the power electronics. It's starting with DC, then it gets to a square wave, then it gets to a triangular wave, and then it just kind of chops it back and forth according to a timer. Instead of just implementing rotatory motion from something like an arc, plasma, the fourth state of matter, instead of just having an axle that spins and then converting that directly into the smooth sinusoidal alternating current, which all the devices that plug into the wall are designed to work on, or power conversion here. Has a thing. This is a sort of idea how to make one of these. Then with like an auto transformer, it just taps all the way around, and it ends up making things. Vis-a-vis like taking just direct current and put it in using signal integrators, and that you can basically get out of like a square wave to a triangle wave, and then to something that's kind of closer to a sine wave, before then just getting it into exactly as close as possible to a sine wave curve, and then one phase current, three phase current usually, or with regards to however many phases you want really, but according to the cycles of the main there, the mains voltages or mains current. With regards then to under and over current and voltage protections and this kind of thing, that you can just put in DC and get out AC, and then just shape that how you want with a variable transformer or variac. Then the idea of these, the Gilbert cell, and then also the Fourier style analysis is that kind of, the idea is that these are ideal circuits, and they're lossless circuits, meaning their efficiency is about 100%. So this thyrototron is theoretically 100% efficient, which is more than any other inverter setup I ever heard of in the world. So it would be better. And so that's the kind of thing. And then this idea of the Fourier style analysis is like, well, just use the same lessons from Fourier style analysis to do DC to DC conversion. Because otherwise you kind of got the auto transformer. The transformer is very well understood and it's according to fractions for AC conversion. But power regulation and power conversion is kind of a particular field. So the thyrototron is a great little idea. And then with regards to that involving shielding or what, it's not impractical, or at least according to the latest AI of the day, who I told it about. Einstein's Unfinished Revolution: The Search for What Lies Beyond the Quantum. So this is a book from Lee Smolin. I recall reading this, and I don't recall too much gain from it, but I must consider it sort of influence of sort. It's describing, like how to think about it and what is. It says the core of our understanding is quantum mechanics. Well, that's the problem with that for me is I think that's a grainy view of nature, and nature is continuous, nature is smooth, so it can't be. It must really be a continuum mechanics. He says, by 1930, de Broglie, and I'll always say de Broglie pretty much because that's how I was taught that it was said, just like I was taught that it was Leibniz is how Leibniz is said. And I might not always say de Broglie instead of de Broglie, or that was my French pronunciation of his French name, de Broglie. But I'll say de Broglie, and do everybody knowing that Americans would speak it that way. It's fair. The anti-realist Copenhagen interpretation dominated the teaching, and today we know that Bohm. Well, they mention Bohm too. So this is one of the books that's coming back, and it's like, at least acknowledging that Bohm and de Broglie were in their hidden variables or supplementary variables, it's called these days, was not wrong, and the whole Everettian multi-word hypothesis is unfalsifiable, and it just means there's something undefined. Say, a handful developed theories of wave function collapse. Some of these realists are many worlders, but there persists a small community of Bohm-ians. I guess I would kind of consider myself a Bohm-ian because of the pilot wave and the ghost wave. These basically reflect for somebody like Fritz London. The idea is it's like, hey, when a particle hits, if it's going to be a particle at all and it's just kind of a wave, then for it to be a particle at all, it collapses as if it's split from the back and all snapped up to the front of that. And like kind of like a slingshot strap, so if they broke or something like that. And so then trying to figure out what that would be as a real thing, it's like, well, it's a superclassical kind of thing again. It's it happened. It would have to happen instantaneously, or as with regards to orders of magnitude in terms of like gravity speed, or with regards to mass, inertia, momentum, and heft here. That's the pilot wave and ghost wave would then count me among the Bohm-ians, I guess you might say, and realists. And then he talks about like Stephen Adler and Gerhard de Hooft, and so de Hooft is like, he kind of gets there. I mean, he's like, well, we want to take all these philosophical aspects and also to get to some of the experimental aspects, and then I'm going to make this ladder stuff. And it's like, that ladder is still just discrete again. You might as well just call yourself a string theorist on this ladder on the way to string theory. I mean, it's not continuum mechanics. It's not continuum mechanics. And if it's not continuum mechanics, it's not a proper quantum mechanics. Not everyone working on quantum foundations accept the conclusion of Bell's theorem that locality is violated in nature. Well, it's not if it's just super standard. I mean, that was a standing state, and when it goes, and it's, as a standing state, it's an extended body. So as a particle, it's either the point and has zero extent, or is not, and it has non-zero extent. So superdeterminism then still has the matters of influences and these kinds of things and preferences still make for so that free will is a thing, even if there's superdeterminism. What else is in this box? Quantum Mechanics 2, a second course in quantum theory. Ruben H. Landau. So this is Landau from like Landau and Lefschetz and this kinds of things. This book prepares readers who have had exposure to quantum mechanics to read primary sources. See, it cost me $70. It's Quantum Mechanics 2 out of Oregon State University, a Wiley Inner Science, published in 1990. So it's got scattering, time independence and time dependence, 1 and 2 body Schrodinger, coordinate systems, and elastic scattering. So scattering and tunneling. so this is scattering and tunneling and virtual photons, I imagine. Waves, low energy limit, scattering, definition of Green's function into eigenfunctions, spectral representation, and these ideas that then make for out of the infinite and the spectral and the continuous, the finite and discrete. The Neumann series. So the Neumann, Carl Neumann is an underappreciated physicist. And so he is from the late 1800s, and I guess he was a German guy. Neumann. I think it's Carl with a K, but it might be Carl with a C. Anyways, he's somebody to be looked at as very, very much influential, if only tangentially, as having been so correct in the later interpretation of what he has and these kinds of things. Yukawa and Coulomb. It's like, why do we have both Yukawa and Coulomb potentials? Well, we got to do them differently, and so we got to have two. But one's Yukawa works great in this field or sector, and Coulomb works great in its field or sector. Partial wave, Green's function. Well, this is like, well, we got all this stuff, but we were told to just shut up and compute. So like, well, here you go. Here's something that you can crunch. Hartree-Fock, yeah, Hartree approximations. I've heard of these things. Thomas Fermi theory, Thomas Fermi Dirac. Bethe Goldstone. So the Goldstone bosons that's like getting to where it's like, well, we got Goldstone bosons, and so we're not quite sure if we got like nucleons or neutron theory or Higgs or boson theory. And Higgs was like, oh, I'll explain Goldstone bosons for you. It's like, well, yeah, yes and no. We might not be. I'll be quite electrical as that. Lorentz transformation of wave functions. So that's just like get it back invariant however it goes. And here that's space contraction. And the space frames and the frame spaces here for the spiral waves and wave spirals. Occupation number. So this is the field number formalism is like, well, it's all fields. It's like, well, all we got is particles. Well, we'll have a field number formalism and say everywhere in the field there's a particle. It's like, well, how grainy is that? It's like, well, we don't say. I mean, it's one or the other. One of the difference between point and space in the geometry. So this is a book that covers kind of 1990s view of the world of quantum mechanics. Okay. This is going to take a while, I imagine. A Literary Companion to Science, edited by Walter Gratzer, Gratzer, Gratzer. Science is a cultural activity for which the 20th century will be preeminently remembered. Gathered from literature, biography, reportage, and poetry, here's a highly readable collection of the images of science. A Literary Companion to Science. 1989 by Longray Group, first American edition 1990. There follows a tale of von Kempelen and his discovery with a related theme by Edgar Allan Poe, who published a series of scientific short stories, densely written and formidably well informed, according to the wisdom of the time. Von Kempelen has come upon a diary of Sir Humphrey Davy, and there found a momentous observation. So this is just an excerpt, imagine. Gravel, with only 1 part in a million, has been worked properly, and even on the Rand, the quartz only averages 12 parts in a million of gold. So science and all. Numbers. Id, ego, and superego, and Father, Son, and Holy Ghost, mentions of things. Have you already forgotten your physics? In 10 years? Just think of all the things that are transparent seem not to be so. Paper, for instance, is made up of transparent fibers and is white and opaque only for the same reason that a powder of glass is white and opaque. So this is like the millet seeds or whatever, and do they make a sound and this kind of stuff. Talks about colors. Here there's a theory of colors. It's a little bit double. What is the theory of colors usually? Literary approaches and treatments of scientific subjects. The literary arts. Oh, this is good. This Elimar is E, the story of a number. So this is about Euler's constant. And so then this Elimar, he already had this other great book called the Beauty of Geometry, the Beauty of Mathematics, or something like that. And so that's a great coffee table book. It's Maor's book about the beauty of geometry or something like that is a great coffee table book. But this is about E. So of course he starts talking about John Napier and the logarithm. So I just wonder who had come up with the logarithm before Napier, a Scotsman or so. And then later the Euler picked it up and made so much to do with it after de Moivre because of Euler's identity and all this stuff, which is just kind of like it's kind of like a principal branch, but it's also just kind of like an inner route or path, to end up that it's like, well, it just kind of spirals down to the origin, but you can just keep widening it and multiplying it out by another one, and then it spirals out and then flat again to a line. The Euler's identity and the spirals and these kinds of things, or the representation of spirals in Eulerian form. So before Napier, though, because the idea of the logarithm is like, well, we know like when two numbers times each other is this, and two numbers to their powers then is kind of like this. It's like, well, what's the inverse of that? And so that's the whole idea of the logarithm is, well, what is the inverse of that? And then to work up stuff like the addition formula, it's like, well, then given those, we can invent a slide rule and make the markings on it so you can compute with that just by sliding the rules and seeing that the lines match up because of the addition formula and these kinds of things and the table of logarithms. And so there must have been that before. I'm just wondering. I'm not quite sure to say who we could really point to as having that kind of idea overall. Because then it's also sometimes before that they'll have the idea of the generical or the generic, and then make the abstraction, and then make the specific of that. Or they'll invent this. Somebody will discover the specific first, and then later make the abstraction, and both. So trying to figure that out is for the general and the abstract, and the specific. The pure and the applied, say. But the general. Leibniz's notation, mechanics, the differential equations, the presence of the exponential and the natural logarithm, all of the differential equations, because it's differential or its derivative and its antiderivative are all the same. It's kind of a constant under that. Then he's got to talk here between Bernoulli and Bach somehow. Talking about tones. A spiral. The 12 notes of the equal tempered scale arranged along a logarithmic spiral. So, yeah, Maor says that, and there's been lots of looking at the notes because the notes are tones or semitones are... that the octave is twice the frequency, say. So that it's split out and down in terms of like the chromatic between those and the I don't know so much my Lydian scales or Mixian scales or Stygian scales and these kinds of things. But in the theory of music, it's so representative that then to have all these different things. Then it's another way to visualize this stuff. That there's plenty to look at with regards to music theory and these kinds of things. Oh, in the catenary, this is a challenging thing. Oh, this is the e to the x plus e to the minus x over 2. And so this is the beginning of the double power series in the exponentials. And furthermore, it's this x squared minus 1 bit, a bunch of different things with regards to the big end and the little end, and then those of the series being the double series. That the double series is even cooler than the series itself. So this is a pretty great work, and it's enriching and it's enrichment. Martin Gardner, Penrose Tiles to Trapdoor Ciphers, and the Return of Dr. Matrix. So Martin Gardner is a well-known popularizer and regular contributor to Scientific American, if I'm not mistaken. And this book was published in 1989. He dedicates it to Roger Penrose for his Penrose Omninos, all his different tiling patterns. He says Penrose tiling 1 and 2, Mandelbrot's fractals, Conway's surreal numbers, Back from the Klondike and other problems, the Oulipo 2, Wythoff's Nim, pool ball triangles and other problems, mathematical induction and colored hats, negative numbers, cutting shapes into n-congruent parts, trapdoor ciphers 1 and 2, hyperbolas, the new Eleusis, Ramsey theory. I'll look to Ramsey theory. I was going to look to hyperbolas here, but Ramsey theory. This book is a collection of Scientific American columns that I wrote over a period of 25 years. Signed, Martin Gardner. So Ramsey theory involves the difference in the powers between 2 and 3, and when it gets to, and it's framed in terms of graph theory and coloring, because in the small and the combinatorics, it's like, well, they would be the same, but in between 2 and 3, it's like, well, it would be different, and then getting these things. Although a few papers on Ramsey theory by the Hungarian mathematician Paul Erdős and others appeared in the 1930s, it was not until the late 1950s that work began in earnest, and the search were now called Ramsey numbers. So Erdős introduced the giant monster of independence, which is about, here it's about these laws of large numbers, and it's independent standard number theory, many various conjectures in number theory. So Erdős called this the giant monster of independence of number theory. So at least that's kind of well known that mathematics always already has these ways out, and that like when you see something like, well, so and so proved this latest thing, and they decided very simply, like, this whole other branch of mathematics was wrong, which for whatever reason they were working on for 40 years. And it's kind of like, well, actually, it's independent. And so what you're looking there is a distinctness result instead of a uniqueness result. And so what you're looking at there is the need for mathematics to revisit how it got there. And so that, yeah, both of those are so. These kinds of things. Well, gentle readers, I've talked my way through another hour of this, with the idea being it's sort of, a few books from a box, almost entirely that it would take a day or two, just reading at speed. It usually, for somebody who's practiced a lot and read a lot and reads a lot, to kind of read all these things. But it helps to describe and show that there's these relations in these things, the numbers and all these matters. Then for the practical and the applied, that are totally enduring, and are they worth the effort to learn, for that their application can provide the value of them? Yeah, no, I'm not too sure. But I know for pure mathematics that having the best theory of all is kind of considered good, even if it's just for people who would do that for its own sake, just for the matters of truth and that kind of stuff. About the infinite, and then continuous and discrete. That's mathematics for you. So good day, gentle readers and fellow earthlings.